to move to Ulrich, who is going to talk about the automated ICS vulnerability assessment. And I'm also going to spend a couple of seconds on sharing a couple of interesting things about Ulrich. He received his PhD from the University of Cambridge Computer Laboratory, the security group, on conceptual aspects of middleware security back in 2003, and it was sponsored by the UK Defence and Evaluation Research Agency. He also completed a master's degree in information security from Royal Holloway College, University of London, back in 1997. And he's currently working on an intelligent big data supply chain risk analytic solution and other various projects around policy automation and policy testing. He's also on the board of directors of the Cloud Security Alliance. I think all of us know CSA. And is a technical expert witness. He's also responsible for the development of the Open PMF user interface, policy automation, and testing features. And he also runs the US office in sunny San Diego, California. Thanks for being here, Ulrich. The stage is yours.
Thank you. Great. Welcome, everyone, and thank you for having me. So yeah, I'll be talking about automated ICS vulnerability assessment and some current research work we're doing that we're doing for the government and kind of setting the scene a little bit for people trying to get a handle on what's going on with ICS security and what they got to do about it. So here's the one slide about our company. I guess the intro already said it all. We've been working on security automation for close to 20 years. A lot of it related to security policy, fine-grained access control, and attribute-based access control. So that's where this OpenPMF product came out of. In more recent years, we've worked on supply chain risk analysis automation, especially in our Navy project, where we look at IT supply chains, but from the angle from procurement data and shipping data and supplier data and so on. So it's doing this passively versus things like vendor vetting, and also works on microelectronics and boards and parts and so on. The thing that really we're focusing on today is vulnerability assessment and pen testing automation, especially for embedded systems. And that's a government-funded R&D contract. Yeah, I'll be spending a little bit on that. Yeah, I guess I skipped the stuff on the right side since it's already been introduced. And I'll move on to the next slide here. So you look at IIoT cybersecurity, there are many challenges, and I only put a few out there. So one that's a big one is usually there's often outdated vulnerable software on these devices that's literally unpatchable due to whatever, either age or lack of access or lack of network connectivity or manufacturer not giving you access and so on, right? So usually people don't think of these things as having to do regular updates on those devices. At the same time, embedded devices aren't really kind of PLCs, logic controllers anymore. Quite often they're now really full-fledged computers in recent years, and it's going to continue this way. So there's a lot of functionality on those devices, a lot of software and a lot of unused software too. So that makes it really challenging to get a handle on cybersecurity there. Yeah, I guess there's lack of risk assessment and risk management knowledge for IIoT, especially for embedded systems. What I mean, for example, is we have pretty well-established libraries like CVS, the Common Vulnerability Enumeration libraries for normal enterprise software and systems. We don't really have those so much for embedded systems. That's a really challenging situation that basically the standard, if you will, if you sum it up, the standard way for the cybersecurity industry to assess vulnerabilities doesn't directly translate, the tools and the knowledge doesn't directly translate to IIoT, unfortunately. So that's really a problem. And then I guess the physical access to the hardware is a cybersecurity issue in the sense that if I can grab the device and open the device, I can potentially get a lot of stuff, to more stuff than a hacker would be remotely on your whatever servers and so on, which they can on embedded devices too if they have network connectivity. So there's a lot of problems there. What we often see too is weak encryption compared to like laptops and so on, or computers, full-fledged servers, due to, especially in older devices, due to the limited resources that are like as in processing power, memory, and so on those devices. And then monitoring is often not really timely, or isn't even there at all if devices are essentially put somewhere and left. You know, quite often you don't have the connectivity to really do some real-time monitoring on it. So anyways, the list would go on for a long time, and I'm stopping here, but it's a huge topic. So there's a lot of problems, and a lot of companies are resolving those. So it's not like it's all doom and gloom. But I think what's really important is that IIoT and especially embedded systems, there are a kind of different space from traditional, if you will, computing, like enterprise kind of normal computer computing, right, or server based. So that is just important for, I guess, the cybersecurity community to understand. So one of the questions that we've been tasked to look at was, well, how to check if IIoT devices are vulnerable? You know, so there's many ways of doing it, and we already had a presentation earlier, and we do something else, and I think there's a combination of many things that need to be done. But like the challenges in order to check whether your device that you may have already deployed years ago and not updated is vulnerable or not, it's challenging because often they're already deployed, right? So they're already on some, say, well, we're dealing with the government, so on a ship, for example, they would be deployed on a ship already, and you know they're there, but you don't know, you know, it's not like you can just unplug them and take them home and analyze them, you know. So often they're like actually truly embedded in a device, you know. There's often no screen or keyboard, but the only way to interact is through either a console terminal type thing where you plug in, or through a diagnostics port like UART or JTAG or other ports that the manufacturer put in for diagnostics. They're often proprietary in their nature, as far as what they communicate with you. Logins are often unknown. So we've seen this, for example, in medical devices, where they either default, so everyone knows them and you can get them on Shodan, or they're unknown and only the manufacturer will use them for their own servicing. So you will not be able to get in unless you break in. And device internals are often unknown. So quite challenging. So how's it done today? In our experience, it's basically people doing it. People go plug in, break into the device, extract the firmware, analyze it, and create a report. These people are scarce, expensive, and yeah, there's just not enough talent out there, you know. So our research question was, can this be done simpler and cheaper, especially for devices that are already deployed? And what we're developing is called VAPT. VAPT stands for Vulnerability Assessment and Pen Testing, and it's supposed to be an automated VAPT, like Vulnerability Assessor and Pen Tester. So basically a portable device that non-experts can connect to IIoT devices already deployed in the field. The device then, if you will, breaks in, extracts and analyzes the firmware, and provides an easy to understand result. One of the kind of, that's already all pretty challenging to build, but one interesting aspect of the use case is that we use deep learning to predict and learn over time what works and what doesn't work, kind of like one of those human assessors. As they get more mature in their career, they learn kind of sequences of things that work and don't work. So that's we already built quite a bit of this. So this is a working advanced running prototype. And we got several years to go in this project to get it to a stage where it's going to be polished, basically. I think there's what I want to focus on is there's multiple ways of getting into a device, because that's really where it's all different from the usual software analysis, where you provide your binaries or you install an agent or whatever. Right here, the question is, how do you even get in, right? So device ports are usually, you got things like USB and sometimes memory card, like SD card slots and so on the exterior, and network, obviously, which I'm going to come to later. But you also have internal ports on the board, like UART and JTAG, that are serial ports, and these can be used. Sometimes they reveal a console for you, right? So the BAP box in this mode, if you will, probes ports, so you can plug it into the diagnostics ports on the board, and executes a sequence of actions. The actual assessment actions, once it's able to extract the firmware, they're in our case, they're using mostly open source vulnerability assessment, binary vulnerability assessment tools that be encapsulated in containers, and we run those, and they're basically not easy to, not intended for automation. So they're meant as tools for experts. So the kind of output you get from those tools is intended to be native to the tool and understood by an expert as part of their analysis. So one of our main pieces of work was to map all this output back into a common nomenclature. In fact, we use CWE and not CVE for the reason that CVEs don't really seem to exist very much for embedded devices. So a CWE, common weakness enumeration, is the basis, if you will, the metadata of a CVE. So a CVE talks about a vulnerability for a specific kind of software version, for example, and it has an underlying weakness that it pertains to. So say a weakness for a specific, say, Apache server version or something like that, right? The underlying weakness is independent of the specific technology. So it would be something like unbounded string, unchecked string copy, buffer overflow risk or something like that, right? So we map to CWE, and then we essentially run analysis over the bulk of tools. A real challenge here is that our device is supposed to be a battery-powered offline device that you can bring to the embedded system. So this is where it's really radically different from most other technologies out there, because that limits dramatically what you can do. Things like dynamic binary code analysis, binary analysis, they take usually a long time. They take a lot of processing power. So you only have a certain time before you run out of battery or out of time before, and then you got to find a result. So it's a pretty specific use case. The reports also are supposed to be for non-experts. I mean, think of a fancy traffic light score, right? And then when the device has connectivity back, it goes back to a backend and everything gets analyzed and the AI runs and so on. So this is really the hard piece here. And frankly, even breaking into a device, especially if it's at the military or government, is relatively challenging because these ports are often tamper-proof. So you can't just run your pen test on a diagnostics port; it'll lock you out. So we do have a bunch of remaining challenges there. But for commercial off the shelf, this works pretty well by now. Via networks, it's easier. We've actually done some R&D before that for also a different government agency. Kind of follows the same idea that I've described, but instead of having to plug in anywhere, you just sit on the same network. And in a way, it uses, for the cybersecurity crowd here, it uses everything that Kali Linux can do, but automated, right? So there's a bunch of there are a bunch of people out there that have done this kind of network-based automated pen testing. It works better or worse depending. So we got that working too, and it's actually way easier than the vulnerability assessment, because all you do is probe, well, port scan and do things like that, right? Nmap, port scan, and also on the network, the CVEs apply, because a lot of the stuff that's on the network from an embedded system would be things like a web server for your admin console, for example, and that uses standard components, usually like a lightweight web server of some sort. But same flow, if you will. And I'll leave it at there, because I'm sure there will be questions. We do have a demo video online. The whole thing's really in a way a collaboration, because we're talking to many vendors in the space and many open source teams that provide vulnerability vulnerability assessment. There are literally hundreds of tools out there, and some better supported than others, and some overlapping in scope, and some adding to each other's scope, and so on. So it's a majorly challenging space, as also evidenced by the DARPA Grand Challenge that happened a couple of years ago, where several teams showed up in, I think it was Vegas, with data, each kind of a rack-mounted data center on stage, and ran through a bunch of binaries to figure out who can find most vulnerabilities in the shortest time. Now, that we use some of those software components, but that's kind of easier if you have a data center. It's extremely challenging once you have a portable device. And portable here, by the way, means briefcase size or something like that. It does not mean iPhone size, you know. So we just want to make clear there's probably no way to really assess the binary without external knowledge, and we were supposed to do this without signatures, without software bomb, without any prior knowledge of the device, basically. So that drives up CPU and requirements and memory requirements substantially. So these sound like mundane challenges, okay, dealing with performance and so on, but they do matter critically when you do vulnerability assessment. And that's me. Here's my email. You can find me on LinkedIn too, and I'd love to discuss it more. And I don't know if we have time for Q&A.
Yes, we do. Thanks a lot, Ulrich. Really interesting. Let's start with the questions that popped up. What is missing in the current OT security solutions available in the market? So basically, what's the differentiator, I guess, of VAPT box?
Yeah, so like I said, typically you don't have a portable device that you can bring to the embedded device that can run battery powered without any prior knowledge of the embedded device, and in many cases give you a result. That's really the big differentiator. Now, if you have access to your firmware, then you unlock and you can go to numerous other solutions. But if you don't have access, getting the assessment to the device versus the other way around is one of the big differentiators. Also, looking at these tools out there, you do have to have a level of expertise in order to make those work for embedded systems. So, you know, you can use, there are many tools like anything from, well, I don't know, Anger to AFL to, you know, I don't know if people know those tools. I'm just throwing out a few buzzwords, but these are open source tools for vulnerability assessment that really require an expert to operate. So to automate those, it's really there's a gap in the market at this point. I think all solutions that look at binaries that we're aware of, they are usually SaaS based, and usually based more for enterprise type CVEs. They're very good at taking your Unix binaries or Windows binaries or whatever it is and analyzing very, very elaborate, great analyses. So this is kind of a niche, IIoT embedded niche issue here. Should also explain maybe the use case for our customer is to be on a ship that essentially may not have internet connectivity or may lose internet connectivity while you're keeping this offline service, offline box running to analyze stuff. So it's a pretty stringent use case.